I'm Mark Duginske. I learned woodworking when I was quite young from my father, who was a pattern maker and a cabinet maker. He was taught by my grandfather, who was a cabinet maker and a builder, and he was taught by my great-grandfather, who was a builder and a logger. He came to America to work as a young man in this virgin timber in northern Wisconsin. Most of us will never have teachers like these guys. Today, most woodworkers are self-taught, which is fine if you have the time, but it can also be very tedious and very frustrating. What's frustrating are the things that are not obvious. The miter gauge that's off just a hair, or the tension inside a board. The key to satisfying machine woodworking is a systematic approach that helps you control some of the subtleties. I really hope that this video will help plane some rough material off your learning curve. Let's start at the beginning with the first step in stock preparation. In standard commercial milling, trees are squared up and then sliced into boards by a large circular or bandsaw. Unless there's a special order involved, the log is sliced straight through without regard to the way the grain pattern falls in the boards. So some boards come out as plain sawn or cut pretty much tangential to the growth rings. Some are quarter sawn, cut radially or at close to a right angle with the rings. And others are width sawn, falling somewhere in between. The boards are then dried in the open air or in a drying kiln, or a combination of both. As the wood dries, it shrinks, but it doesn't shrink uniformly. One of the most common ways wood warps as it shrinks is seen in the characteristic cupping of a plain sawed or width sawn board, concave toward the outside of the tree. The reason this happens is interesting. After a tree is cut, its cells start to lose water and shrink. They shrink mostly in this direction, along the circumference of or tangentially to the growth rings. They try to shrink the same amount radially, but are restrained by the ray cells that form structural reinforcement in this direction. In a plain sawn board, the rings stretch across the width of the board, so a lot of cell shrinkage accumulates in this direction. There's more of this tangential shrinkage in the bark side of the board than in the side closer to the pith, so the board cups this way. In quarter sawn lumber, the tangential shrinkage accumulates only over the relatively narrow thickness of the board, so there's little overall shrinkage and it's pretty much the same throughout the board, so there's very little warping. Plain sawn and quarter sawn lumber can also bone crook because of growth stresses in the tree. Our first job in preparing lumber for woodworking is to remove these distortions. This is a typical board right out of the dry kiln. It's got a slight bow here, a little bit of a cup here, and it's got a little bit of a twist. You can tell that when you rock it on a sawhorse. Face join the board with the cup or concave side down, taking light passes. Use a push stick or a hold down at the end of the pass. You can deepen the cut to about 1/16 of an inch after the first corners are established. With a cupped board, you'll first establish a level perimeter of material that will let the board rest solidly on the planer table. Start with downward pressure over the entry table and then shift pressure to the outfeed table. You don't have to flatten the entire face on the joiner. The leveled face rests on the planer table. The planer will now surface the top face of the board parallel to the jointed surface. Actually, the names jointer and planer are a little misleading because it's the jointer that creates a first truly plane surface. The planer makes the second surface parallel to the first. With both of these tools, it's important to think about the direction in which you feed the board if you want to avoid tear out of the wood fibers in the cut surface. The V pattern on the board's face points the way. Read it in relationship to the end grain pattern. The old hand plane rule is, on the inside of the board, the pith side, plane with the points. On the outside, the bark side, plane backwards or against the points. Of course, with a mechanized planer or joiner, the feed direction is 180 degrees opposed to the direction of the spinning blades. So even though in this case it's bark backwards, you'll feed with the points. Occasionally you'll find the V's pointing in opposing directions on the same face. You'll have to study the surface to decide which feed direction will minimize tear out. One clue is the steepness of the grain seen on the edge of the board. Very steep grain is certain to tear out if you plane against it. Also, if say 80% of the grain points in one direction and only 20% points in the other direction, go with the percentages. When you've completely surfaced the second face, flip the board and finish up the job you started on the joiner. I'm looking for the concave side because I'm going to joint and square the edge of the boards next. Here is the end of the board that I want to take to the joiner first. The grain points in this direction. The cutter head knife rotates and will take little cuts in this direction. And I want the grain and the cutter knife to point toward each other. A good analogy is patting the hair on a dog. If you pat with the hair, it'll be nice and smooth. If you pat against it, or if you cut against the grain, you'll chip it. The concave board rests on its ends, so the ends get cut first. The blades may not cut in the middle at all. Feed the work slowly and evenly over the cutter head. If the grain changes direction, you may not be able to avoid tear out entirely, but a lighter cut might help. Here I'm cutting with the grain. And here the grain reverses, so I have to cut against it. This is getting better. This is what you want to see when you're done surfacing three sides of a piece of rough lumber. The two faces are parallel to each other, and one edge is square and straight. Check for straightness by mating one piece against the other. Check the edges for being square by mating two edges together and then reversing one board and then the other board. Any error will be doubled. These boards had an agreeable concave edge which rests nicely on the joiner table. Occasionally you run across a board with a convex edge, and if you mark the high spot, you can work directly on it at the joiner. Just wear away the high part of the edge, being careful not to push down on the guide with the workpiece as you draw it back each time. That's what you want. But even in central Wisconsin, things don't always work out perfectly. If you don't tune your joiner and your planer to close tolerances, they'll leave telltale defects in your workpiece. This is one of my father's joiners, an old homecraft with an adjustable outfeed table. And here comes one of the most nagging problems with the joiner. You run the edge of the board through with perfect technique, and then the end is sniped. This has nothing to do with wood or your technique. To understand it, first look at how the joiner is set up when all works well. The joiner has four critical parts. The cutter block, made up of the blades carried in a rotating cylinder, the infeed table, which you can set variably some small distance below the top height of the blades as they spin around. The outfeed table, which should be set at just the same height as the top of the blade arc. And the adjustable fence, usually set square to both tables. A board is pushed along the infeed table until it encounters the blades. They cut away a 1/16 of an inch or so, and the cut surface then rides out on the outfeed table, which is set at exactly the right height to receive it. When there's enough board over the outfeed table to get a hand on it, you move your downward pressure here, while you keep feeding with forward pressure from the infeed. In the snipe situation, the level of the outfeed table has fallen below the top of the blade arc. Actually, the outfeed table might have stayed put while the blades were set too high. It's only the relationship between their levels that's important. The same problem will result. This time, as the board comes through, it doesn't find the outfeed table waiting to receive it at the proper height. First, the board rocks slightly onto the outfeed table as you apply downward pressure to it, and the blade digs in a little bit deeper. Now the work is supported only here, where the leading corner contacts the outfeed table, and here at the end of the infeed table. As the tail end of the board passes the end of the infeed table, it falls off, down to the level of the outfeed table, and the blades snipe out a hollow at the very end. Here's how to eliminate snipe. In a test piece, I made a cut about 4 inches long to determine the height of the cutting arc. Raise the outfeed table until it's even with the cut. A thin feeler gauge will help you know when you're getting close. Another common defect occurs when one knife is higher than the others. It will do most of the cutting, creating a waveform. The solution is to set all of the knives at the correct height. The first steps in stock preparation got us 2 flat faces and 1 square edge. In order to get the final edge parallel, we've got 2 paths that we can take. If the boards are narrower than 3 inches, you can run them on edge through the thickness blender. Wider boards are less stable on edge, so boards like this that are 6 inches wide, I'm going to rip first on the table saw. A lot of people like to use a board like this right off the saw. It's quick, and there's also a fairly popular misconception that this rough, toothy edge makes a good gluing surface. I prefer to join the edge. I think it's more workmanlike, and research shows that a jointed edge makes a better gluing surface. Sometimes stock preparation has to start at the table saw. This is a carriage jig, which is made of 3/4 inch plywood, has a hard maple runner. It's got countersunk holes that accept the head of a carriage bolt. These are hard maple spring clamps. They're thinner in the middle so they flex, and the end has an adjustable drywall screw so they won't slide off the workpiece. Feed slowly and make sure that the spring clamps clear the guard. Some sort of outfeed support is essential. The rough edge will often pull away. Support it so it doesn't tear off at the end of the cut. The first place to look when tuning your table saw for precise work is right here, in the fit between the worm gear and the rack on the front carriage casting. If this connection is kept well lubricated, wear won't usually be the culprit. Don't assume that the manufacturer did a perfect job tightening it. Also, normal vibration will loosen it, so you should check it monthly. You can get a reading of the slop by grabbing the carriage bars or the motor directly and shaking it. But first angle the blade 10 or 15 degrees so that your test isn't affected by the 90-degree stop. The adjustment on most saws is here at the crank handle mounting bolts. Loosen them and then push the crank handle down. The worm shaft casting right here acts as a fulcrum. The worm goes up, tightening against the rack. Here's a little tip. Replace the nut on the other side of the bolt with one of these. It has a star washer attached to it. Or use one of these star washers between your nut and your washer. One more hint. With some saws, no matter how well you adjust the gear and the rack mechanism, you won't be able to take the slop out. Older saws often have a device called a trunnion lock, which clamps the front trunnion and carriage casting together. You can do exactly the same thing with a C-clamp. Just snug the trunnion and the carriage casting together. Next, I'm going to lubricate the inside of the saw. I like to use this white lithium grease, which also has Teflon in it. This nozzle is great because it makes the application so easy. Other greases and heavy oils attract too much dust and gum up. Dry lubricants such as graphite and silicone don't have the body to hold up well in this sort of dusty environment. When setting the blade's 90-degree stop, place a square on the side of the table slot with the least amount of throat plate. Back the blade away from the vertical about 10 degrees. A good trick here is to use a flashlight to help you see very clearly when the gap between the blade and the square has completely closed. Start cranking up the blade, and when the stop bolt lands against the end of the worm drive, if you can see light, you've got some adjusting to do. Crank away from the stop and loosen the lock nut. Adjust the bolt by trial and error until the blade's square to the table, which you'll know when all the light is blocked by the square. Next, lower the blade all the way to adjust the table insert or throat plate. The edge of the square is now at the level of the tabletop. Raise the throat plate until it's just a hair below the tabletop in the front, so that the end of a board doesn't run into it when it's being fed into the blade. In the back, the throat plate should be high by a hair, so that the board doesn't catch on the edge of this table slot behind the blade. Now we adjust the miter gauge. This bar has about 12 thousandths worth of play, which is way too much. To adjust the bar, remove the head and then position the bar on a piece of wood on the top of the table. Use a prick punch and make small indentations to expand the width of the bar. Stagger the indentations so they aren't all in the same line. This will limit the wear on the cast iron table. Go all the way to the end and then test the fit. You may need to try 2 or 3 times to get what you want. Almost no side-to-side play. Just deepen the first set of dimples and keep trying. If this fit were too tight, I'd just file it down a bit. Wax the top and miter gauge slots with a good furniture grade paste wax. I do this every month or so as a regular part of my table saw maintenance. Next, put a square against the miter bar and make sure that the head is set at a true 90 degrees. Now attach a straight auxiliary fence with screws through the holes cast in the miter head for just this purpose. This gives better support to longer boards than just the narrow miter head. Remove the throat plate and bolt the guard in place. This basket guard bolts in 2 spots, inside the saw slot behind the blade and to the rear of the table over the motor mount. Carefully align the splitter with the saw blade using a straight edge and adjust the guide's mounting bolts as necessary. Before locking it in place, make sure you've squared it up with the table. Now I'm going to make a simple test. With one cut, I'll be able to confirm all the setups that I've made on this machine. Place an X on the board and cut the X in half. The two pieces will go back together tightly. Now reverse one face to test the blade to table for squareness. Standing the boards on edge, test the blade to miter for square. It may appear as if I'm just playing with blocks, but these 3 blocks are really a sophisticated dovetail jig that will do the same work as jigs costing up to $300. Each block spaces a table saw cut from the corner of one tail to the corner of the next tail. The tail and the block in the middle are bigger than the ones on the outside. The total width of the workpiece is 4¼ inches. The total width of the blocks is 4 inches. The difference between the two is 1/4 inch, and that determines the size of the half pin and also the size of the full pin. There are 2 other parts of the jig. A piece of plywood 4 inches by 24 inches and a stop block with sandpaper glued to the back of it so it doesn't move. I'm going to make a dovetail box. I've numbered the sides consecutively as they were cut from the board so that the grain will flow around the box continuously. And the gauge line is set back from the end of the board a distance equal to the board's thickness. Now I'm going to mark a setup board using the spacer blocks. These marks will help me align the work for the first cuts on the tailboard. Now the blade comes up 2 or 3 inches so I can set its angle to exactly 10 degrees with a simple angle gauge I made. The blade moves down below the gauge line about 1/8 inch. I place the test piece in the proper position, aligning the mark against the angled blade at the very bottom of the mark. Now I clamp it temporarily while I bring the blocks into their proper starting position. Don't forget to accurately square up the stop block. The spacers move into position. Plug in the saw. My right hand clamps the test piece while my left hand secures the blocks. The blade splits the mark at the bottom. I carefully inch up the blade toward the gauge line until it just touches on the high side of the blade. Okay, that's real good for the test piece. Now we're ready to work on the tailboards. And make the first cut and then rotate the board. And now I rotate it end for end. So I make a cut in each of the 4 corners with all the blocks in place. Now I remove one block and repeat the same series of cuts all the way around again. It takes about a minute to cut the tailboard. Notice also that I take 2 passes. This guarantees that I'm removing all of the waste. The second block then comes out. The third series of cuts crosses the second series, completing the sides of the dovetails. I'm going to remove the waste on these tail boards using the 1/8 inch blade on the bandsaw. My goal is to cut right down the middle of the gauge line, and to do that I'm going to use this micro adjustable fence. The adjustments are made with paper shims, which are 4/1000 of an inch thick. The fence is very simple. It's just 3 oak boards bolted together. There's a piece of sandpaper in here that prevents this piece and this piece from rotating in relationship to each other. This board is bolted to this base with 2 bolts. There are wing nuts here so that I can either add or subtract paper shims. In this particular setup, I'm going to subtract paper shims. No matter how good you are, there's no way that you can consistently cut a knife line in half. So I've set up the fence so that the cut is off the knife mark by about a 1/64 of an inch. To sneak up on the mark, I'm going to remove shims, which are 4/1000 of an inch thick, about the thickness of one of my beard hairs. This is what they mean when they talk about moving something just a hair. It's perfect. You can waste a lot of money on gadgets and gimmicks and doodads and all these things that promise accuracy. Some will promise that they'll be within a 32nd of an inch, and that sounds awfully good until you figure out that a 32nd of an inch is really 8 of these. This is real precision, and it really hasn't cost you very much. You can spend your money on better things. You could buy a decent router or more bandsaw blades or a decent table saw blade. This is precision, and it costs you almost nothing. Besides, you can write notes to yourself, or you can take phone messages with these things. Now that we've got the fence set, we're ready to finish up the dovetails. The waist where the half pin will fit comes out easily. Guide the saw kerf over the 1/8 inch blade. The tiny triangle of waste to the right of the blade keeps it from lining up with the knife line. But don't worry. Just snug the workpiece against the fence and cut into the opposite corner. Flip the workpiece, slide it back in, and clean out the initial form. I made the tail board with one setup on the table saw because one side's a mirror image of the other side. I don't have that advantage with the pin board. Now I'll need to make 2 setups, one with a miter gauge angled 10 degrees in one direction and then 10 degrees in the opposite direction. First thing that I'll do is tilt the blade back to the 90-degree position. To set the miter gauge at 10 degrees, I'll raise it up out of its slot with some pennies. And then adjust it with that same little homemade 10-degree plywood angle that I used to set the blade for the tailboard cuts. I reposition the blocks, loosen the stop block, and then line up the blade with the inside of my start mark. I then bring the blade a safe distance below the gauge line for the first cut on the test piece. Make the cut just inside the pencil mark. Then raise the blade in 1 or 2 passes until it cuts the gauge line in half. With the test piece all set up, I can start the first cuts on the pin boards. Two cuts only for the first block. Then remove the block, make two more cuts parallel to the last two. Then the second block comes out and the last two cuts at this angle are made. Now I'll change the miter gauge around for the second series of cuts. So it's the pennies again. Then I'll set the fence 10 degrees off square in the opposite direction. And I'll use just one block to make my next start mark, this time directly on the workpiece. The micro adjusters go on the stop block now. They'll do their thing in just a few minutes. And I've left out the number one block because the first time I move the workpiece, it will have to be across the distance of the wide center tail. I've deliberately cut the pins a little bit oversized so I can trim them to fit later. This is the pin board from the end. Once or twice I've gotten confused when I looked at it and actually cut out the wrong piece. Rather than cutting out the waste, I cut the pins off. So now I always try to lay it so that the small dimension of the pin is upwards, and I mark the waste with a big X. In cleaning out the waste, there's a little angling trick to learn. You have to lift the front of the board at the entry of each cut to reach all of the waste in the corner of the 10-degree table saw curve, and lift the back at the exit of the cut. It takes a little practice to get the angle just right, but after you've done it a few times, it won't be a problem. Just take your time. Now it's time to fit the joint, and as I expected, it's just a little too tight. This is what removing 4/1000ths of an inch of oak on a table saw sounds like. I should really take out one piece of paper because this is too tight for glue right now. But just to show off, I'm going to squeeze it all the way together. In fact, this is about the only time that people from Wisconsin show off. Although the table saw was designed as a ripping tool, actually it's more accurate for cross-cutting. One reason is that the cross-cut surface right off a high-quality table saw blade is hard to improve on, while ripped surfaces should always be finish jointed or planed. Another reason for the table saw's cross-cut accuracy is that the miter gauge carries the work past the blade. With the miter gauge and an auxiliary fence, you can set a stop that establishes the length of the finished workpiece. And then you can run the whole unit past the blade. With paper shims, you can easily micro-adjust the length of the finished piece. Also, you don't disturb the workpiece as it's moving because you don't have to change your grip or pick up a push stick. When cutting many pieces of stock to length, first establish a good square end, cutting the pieces oversized. This stop block, set back the desired distance from the blade, guarantees that every piece that I set against it will be cut to exactly the same length. The square end goes against the block. When you're cross-cutting, use your left hand to hold the stock against the fence. Never touch or support the wood on the opposite side of the blade during the cut. Always let it fall free. The result of using this simple double stop technique is 3 pieces of wood that are accurate within a couple thousandths of each other. This setup works well as long as the boards aren't longer than 3 feet. Over 3 feet, they become a little bit tippy on the table saw, and besides, there are better tools for longer lengths. The time-honored tool for cross-cutting has been the radial arm saw, but in my shop, it doesn't get used that much anymore because I've pretty much replaced it with this tool. This is a slide compound miter saw, and what it is really a souped-up motorized miter box. It has a telescoping arm which allows a 10-inch crosscut. It will miter in either direction 45 degrees, and there's a mechanism in the back that allows a compound angle cut. The saw is pulled out and lowered into the board and then pushed forward to cut. You have precise control over the cutting length with an adjustable stop and a good support table. This is a commercial variation on the paper shim micro adjuster I use for trimming table saw dovetails. This machine does the 3 tasks that I always use the radial arm saw for: cross-cutting, miters, and compound miters. But it can't take a dado blade and can't be used for ripping. It's not the complete shop in itself that the radial arm saw can be. In the 1950s, the radial arm saw was sold as a one-tool shop. Many people learned their woodworking on it, including me. You can obviously cross-cut with it, but you can also rip and do a lot of other things. Sears sold a drill chuck that you can mount to the end of the motor shaft, and DeWalt even sold a saber saw attachment. Tuning the radial arm saw can be tricky because there are so many moving parts that you've got to adjust in just the right sequence. Raise the arm so that the blade is free of the table, and then lock the motor in the middle of the arm. Check the rise and fall of the arm with your finger on the column. The up and down movement should be smooth without jerks or roughness, which would indicate dirt or lack of lubrication. Pressure on the arm either up or down or sideways should not cause any movement at the column and base junction. The column rises up through a split base which functions as a clamp. The column's motions can be eased or tightened by turning these bolts. Move the arm out of square, then let it click back in and wiggle it to make sure it's seated well. Check for sloppiness or roughness in the yoke mechanism by trying to rotate the yoke and then sliding it. 4 rollers support the motor carriage and slide in tracks on each side of the arm. Dirt or sawdust in the track causes a rough movement of the carriage. Clean the bearings by applying pressure against them as they roll in the track. If you pull the carriage backwards, you won't pinch your fingers. Test the tension on the bearing by pressing your thumb against it as it rolls. If you can stop the bearing from rotating, it's too loose. An eccentric bolt adjusts the bearing on one side of the track. Lubricate the track with a very light coating of a fine machine oil to prevent rust. The column should be oiled with the same type of oil and then raised and lowered all the way to spread the oil. Now you'll need to remove the guard and the blade to do the rest of the tune-up. The first step is to make sure that the arm and the blade are parallel. Tilt the arbor toward the table. Make sure that the pin lock is engaged completely. Use a paper shim as a feeler gauge. Test the table on all 4 corners and in the middle. If you don't get identical readings all around, you'll have to fine-tune the table height. Each manufacturer has a different mechanism for this task, so consult your owner's manual. Squaring the blade to the table comes next. Make sure that the square is not touching a tooth, both top and bottom. On most saws, the lock screws are at the front of the yoke. Free them up and then tilt the blade to square. Recheck the blade after you've tightened these. It may have moved a bit. Start squaring the blade to the table by marking a tooth, any tooth. Set the square at the back of the table against the tooth and draw the carriage forward. The tooth should scrape evenly against the square. If not, loosen the table mounting bolts and tap the table into proper square with the blade. Repeat the test until you have it. There's another alignment problem called heeling, which occurs when the blade travels through the cut at a slight angle. The leading edge or toe and the trailing edge or heel are not perfectly in line. The heel rubs against the wood, making a double cut or a burn. When ripping, it can cause a dangerous kickback. Heeling occurs both vertically and horizontally, which is the point ignored in most owner's manuals. The adjustments are made at the back of the saw where the motor rotates in the yoke. Here is a real simple fixture for detecting heel. It's just a 3-inch by 12-inch piece of plywood with one corner cut off. I use the cut off corner first to measure the horizontal heel. Rotate the blade backwards until it touches the plywood point and makes a noise. Mark the tooth or teeth that made the sound. Then slide the carriage to test the opposite side. If the marked tooth makes the same sound on both sides, then there's no heel in the horizontal plane. Then clamp the long piece of the fixture to the fence and tap it so that it just touches the tooth with the most run out in the vertical position. Then mark that tooth. Just as we did before, slide the carriage back and listen again for that noisy tooth. If there is vertical heel, you'll hear either a louder sound or none at all, depending on the direction of the heel. To adjust out horizontal or vertical heel, slightly reposition the motor bushing at the back of the yoke. Then reset the jig and test again. That's what you want to hear. The same sound on both sides means zero heel. Here's the one-cut test for the saw's setup, using a piece of plywood with parallel edges. Reverse one face to check for blade square to the table. On edge, with one piece still reversed, you're testing for the blade being square to the fence. There are two approaches to using the radial arm saw. If it's the only tool you have, or if you're hauling it to a job site, you can use it for all your cross-cutting, ripping, or mitering. The other approach is to get everything square and leave it there and use the saw exclusively for cross-cutting. Then when you need to make a miter, use jigs or fixtures to hold the workpiece at the correct angle. This simple jig acts as a miter fence. You can use it to cut both sides of a molding. A flange at the back drops into the regular fence slot, and the whole jig is clamped in place. A variation of this jig has a double adjustable fence. It's very handy for cutting compound miters like those in cold moldings. The double fence allows the molding to sit up in the same position it will take between your wall and your ceiling. So it's cut perfectly. When you drill a hole, the wood you're drilling should not move or vibrate. If it does, there's something wrong. This example is perhaps a bit extreme. The real question is, what's the root of the problem? Is it the bit, the chuck, the shaft, or a combination of all three? The simplest solution is to replace the bit and try it again. If your drill press key isn't spring-loaded, tie a string to it so that it doesn't become a piece of shrapnel if you accidentally leave it in the chuck. As you tighten the chuck on the bit, move it up and down so it centers itself. The vibration is gone now, so apparently the bit was the problem. But the bit won't always be the problem, so it's useful to know how to check the alignment of the chuck and the shaft. This is called a no-bit. It's a smooth machined rod that's dead straight, which is important for this test. Lock it into the chuck like a drill bit. Clamp a short, straight piece of wood up against the no-bit and rotate the shaft by hand. If there's any run out, you'll see it in the small space that opens and closes between the rod and the wood. Measure it with a feeler gauge. It looks like 4/1000ths of an inch measured this way. If you've got a dial indicator, use it for a more accurate measure of the runout. Center the point carefully on the no bit. Then zero out the scale. It looks like 6 plus 2 equals about 8/1000ths measured this way. Now I'll check to see if the runout is any different at the bottom of the chuck. And here I get about 7/1000ths. You'd normally expect to find a little less runout as you test higher up. Here's how to get the chuck off if it's not threaded on. Instant replay. Make sure you catch it. Don't let it hit the floor. On the shaft, I'll start again with the stick just to reassure you that you don't need a dial indicator for this test. And here, with the gap closed between the shaft and the stick, I test with a thin feeler gauge. And there it goes. The dial indicator shows a few thousandths more, about 4/1000ths. 4/1000ths is in the high end of normal limits. If it were more than that, I'd either try to get a new shaft or I'd take it to a machinist and have a new end turned. The runout that I got on the bottom of the chuck was 8/1000ths, which is twice the distance, so that's within normal range. So that would indicate that the chuck is probably in pretty good shape. The next thing that I'll do is I'll seat the chuck back onto the shaft and I'll clean it. There's a little trick to seating it evenly, and I'll show you that next. Retract the jaws from the chuck first. Then gently seat the chuck onto the shaft and bring it down to the wood and just press gently. Next, raise it off the piece of wood just a hair, turn the machine on, and apply a gentle pressure. This will evenly distribute the force. You can do more than just drill holes with your drill press. Here, I'm studying a mortise and tenon joint in a door style. I'm using an upcutting spiral fluted router bit at 4,700 RPMs, which is the fastest you should run a drill press. Overlap the holes by about 25% and then go back and clean between the holes. Lock the bit in place about 1/8 of an inch inside the hole and run the workpiece back and forth between the stops to straighten up the sides of the mortise. Lower the bit in 1/8" steps, repeating the cleaning cuts each time until you're at the bottom. The ends of the mortise are rounded, which tells you something about how we have to make the tenon. I'm cutting the tenon shoulders with an 1/8" blade, rotating the workpiece and cutting all 4 sides to the same depth. The miter gauge in the rip fence must be perfectly square. To set up the cheek cuts, remove the stop block and attach an auxiliary fence that you can adjust with paper shims. A waste mortise cut in half is the setup piece. You could measure and mark here, but it's always easier and more accurate to set up directly from a workpiece if possible. Make the tenon oversized by about a 1/64 of an inch so that it can be trimmed precisely to fit into the mortise. Test the fit. Add a paper shim to shrink the tenon. The amount of waste removed is double the thickness of the paper because you're removing that much material from each side of the tenon. A 4/1000 shim removes 8/1000 from the tenon. The blade may deflect a bit here, so when you're close, cut into a fresh piece to test the fit. The edge cheeks are cut the same way until the tenon fits halfway into the mortise. Now we have a square peg and a round hole. I'm not going to square the hole, so I'm going to chamfer the tenon to fit the mortise. The V-block supports the tenon at a 45-degree angle. Paper shims fine-tune the fit. Make a chamfer in opposite corners with one setup, and then reset to cut the remaining corners. That's a good fit. This sort of accuracy can only be obtained with a well-tuned bandsaw. The wheels have to be in the same plane so that the blade tracks well, and you also have to adjust the guides for each new blade. The first step in tuning the saw is to remove the guard and throat plate and then back off the side guides and the bearings. Don't be lazy about the bottom guides in the bearing. The spring tensioner is set for the 1/2" blade that's on the saw right now. With the straight edge, check that the wheels are parallel and in the same plane. The straight edge should touch the 2 wheel rims at 4 points. If the wheels are not in the same plane, you'll have to make another adjustment. The adjustment on this saw is made by either adding or subtracting washers from behind the top wheel. On some saws, it's the lower wheel that moves in or out with a set screw. Adjust the table square to the blade, being careful not to deflect the blade. Find the blade weld and mark it. Then rotate it to the opposite side of the guides. This puts the straightest part of the blade at the guides. Adjust the guide holder so that the side guides are 1/64 of an inch behind the gullets. Fiber and plastic guides are designed to touch the blade, but metal guides should be set away from the blade the thickness of a paper shim. The proper position of the bearings is 1/64 behind the blade, and you can set it there with a piece of paper money folded twice. Be careful not to deflect the blade. Having the wheels in exactly the same plane is especially important when tracking wide blades. This 1/2" blade will find its equilibrium position toward the front half of the tire. Blades that are 1/4 inch or narrower are best tracked in the traditional way, with the top wheel tilted so that the blade tracks in the center of the tire. Just going to make one quick check to make sure that everything's set okay. Now I've got one last thing to do before I start sawing. Rounding the back of the blade with a stone cleans up any rough spot at the weld and removes the sharp corners where metal fatigue cracks start. It also allows you to take a tighter cutting radius without binding. Use a dry stone for this, not a stone with oil on it, because the oil will make the stone glaze and not grind. This 1/2 inch wide, 3 teeth per inch hook tooth configuration is the blade of choice for stock preparation. You can use it for cutting lumber from a log, resawing, making veneer, or just plain old ripping. If you want to resaw right down the middle of a board, first center it as close as you can by eye. Make a shallow cut in the end, then flip the board 180 degrees and make another cut. The center will be in the middle of the 2 shallow cuts. Reset the fence, splitting the difference between the two, and start sawing. Feed rate and blade sharpness are critical here. Go fast enough to keep the saw busy, but not so fast that you bog the motor down. You'll need your sharpest blade for this kind of work, preferably a new one. It's always kind of fun to open up a board like a book and read the story of the growth rings. There are a lot of things that are fun about woodworking, and what I'm going to show you next ranks right up there with hanging drywall and having a root canal. It's changing the joiner knives. The stamped wrenches that come with most joiners don't usually fit the jib bolts very well, but good quality wrenches are a bit too thick to fit into the slot. So I like to grind down one side. The trick is to hold the jib down as you remove the blade. Watch your fingers here. If you can actually see the edge, the knife is dull. This one is pretty well nicked up too. The jib is a piece of milled steel. The face that is in contact with the knife should be polished up a little better than this one. I'll work on it with some 400 grit wet and dry sandpaper until I can see myself in it. Here's how I get the top dead center mark that I've already scribed in the fence. I lower the infy table until the ruler is just tangent to the cutter head. Visually, center up the 1/2 inch mark on top of the cylinder and transfer the mark to the fence above. Don't assume that the knives you got back from the sharpener are perfectly straight. Check them like this and then feel for a burr. Hold the jib down as far as it'll go before inserting the blade. Make sure that both pieces move freely. The easy way to do this next step is with a magnetic jig. Position the jig by aligning its index mark with both the fence center line and the knife edge. The blade has to be free to move so that it's grabbed by the magnet. Tighten each bolt until you start to feel just a little resistance and then back off a hair. The jib should be just loose enough now to allow the blade to move. If you can shove the knife down, but the magnet doesn't bring it back up, then the jib bolts are too tight and you should back them off a hair. When the bolts are snug, but the knife still moves, you're ready to tighten the knife in the head. Start tightening in the middle and then work to the outside. Tighten in stages so that the pressure goes on evenly. Manufacturers recommend removing and replacing only one knife at a time to avoid stressing the cutter head. Check the setup with a 1/1000th feeler gauge. If the feeler slips in between the jig and the table, then the knife is too high. If it fits in between the jig and the knife, then the knife is too low. This looks pretty good. With the jig out of the way, I can tighten the last bolt. And then a final check. Well, I thought that was too easy. I told you that this was going to be a lot of fun. That final tightening raised the far end of the knife in the cutter head just a couple thousandths. So I back off 3 bolts until they're free, and then persuade the knife back down where it belongs. Back on the center mark. Seems okay now. Tighten up once again. And this time I've got it. Okay, so you don't have one of these magnetic gizmos, and you don't even have any friends who have one either. Here's what you do. Have a flat, wide board ready, almost as wide as the joiner knife is long. Loosen the jib bolts as before, and then change the knives one at a time. Align the knife with the fence mark, and then use the board to push the knife edge right down to the level of the outfeed table. That's all there is to it, if the knife sits on springs. Without springs in there to force the blade up to the board, first snug down the outside bolts so that they just hold the knife a little above the level of the outfeed table. Then force down the knife with the board. Here's the acid test for the height of the knives. Set the end of a straight stick right over the end of the infeed table. When you rotate the cutter head by hand, a correctly set knife will advance the stick between 1/8 of an inch and 1/4 of an inch. Changing joiner knives is like tying your shoes. The first time you do it, it's the hardest. Make it easy on yourself. Practice until you get good at it, and like a lot of other things that you have to do in the woodworking shop, it'll become a habit, and you won't even have to think about it.
Here are some more one-hour workshops from the Taunton Press Fine Woodworking video library. In the bandsaw video, Mark Duginske continues to work with his favorite woodworking machine. You'll see Duginske use 4 different blades on 4 brands of bandsaw. You'll see how easy it is to change, adjust, and fold blades.
And twist.
Duginske will also show you how to bandsaw joints that fit and how to make impossible-looking cuts with ease. A well-tuned radial arm saw can be the heart of your woodworking shop, allowing you to make any furniture you want for your home. In radial arm saw joinery, Curtis Erpelding shows you how to create jigs and fixtures for cutting impeccably precise joints time after time. The Cabinet Maker's Table Saw is Taunton's video reference to the precise setup and safe use of this most versatile machine. Kelly Mailer perfects your basic ripping, cross-cutting, grooving, and sheet cutting techniques. he demonstrates safe procedures for cutting both small and very large stock, and you'll see tapering and cove cutting as well in this comprehensive tape. You'll become more confident and more comfortable around your saw after viewing this tape. Fine Woodworking video workshops can also help you learn about wood finishing, furniture repair and refinishing, wood turning, carving, and joinery. To order any of these tapes, just phone toll-free at 1-800-888-8286 and ask for operator number 18.